Hi everyone, my name is Osber Bastani. Today I'm going to be talking about safe reinforcement learning with nonlinear dynamics via model predictive shielding. Recent work has shown that deep reinforcement learning is a promising approach to automatically learning control policies for challenging problem settings. For instance, settings with nonlinear or hybrid dynamics, stochastic dynamics, partial observability, dynamic environments such as moving obstacles, and so on. However, it can be challenging to ensure safety for these kinds of approaches. Things like that a driving or flying robot avoid obstacles or that a walking robot does not fall over. So we're going to be, in this work, we're going to be considering a known deterministic nonlinear dynamical system. And we're going to consider a controller that is a DNN control policy trained using reinforcement learning. And this control policy directly maps states to actions to take in each state. And we're going to consider a safety property, which is simply a safe subset of the environment that we want to stay inside for the entire horizon. So there's been a number of existing approaches studying this problem. One approach is to try and directly verify the neural network policy and basically formally prove that PyDNN is safe. However, these approaches have challenges scaling to high-dimensional state spaces. Another approach is called shielding, and the basic idea here is to compose the neural network policy with a backup policy, PyBackup, that's guaranteed to be safe. So we're going to use the neural network policy whenever possible, but switch to the backup policy if we can't guarantee that the neural network is safe. However, here we still need to be able to verify that PyBackup is safe. Finally, there's also an approach called model predictive safety certification. And it's very similar to shielding, except it chooses PyBackup to be a linear model predictive controller so that it can basically more easily guarantee that PyBackup is safe. However, their approach only handles linear dynamical systems, whereas our goal is to handle nonlinear dynamical systems. And one point I want to make here is that handling these more complex dynamical systems is really important because that's really the setting where we need, where reinforcement learning is useful for dealing with these more complicated systems. So we propose model predictive shielding to ensure safety in the nonlinear setting. And our basic idea is going to be similar to shielding. We want to compose a learned neural network policy, PyDNN, which achieves good performance but might be unsafe, with a backup policy, PyBackup, which may perform poorly, but satisfies the property that it can safely bring the system to a stop, at least from a subset of states. And we're going to call this such a state X recoverable and denote it as by X recoverable. So just to illustrate what it means to be recoverable, consider this toy example where we have a driving robot that's trying to avoid an obstacle. In this case, we'll choose PyBackup to basically just hit the brakes to try and bring the robot to a stop. And if PyBackup can successfully bring the robot to a stop without hitting the obstacle, then the state X is recoverable. Otherwise, it is not recoverable. So the model predictive shielding algorithm is quite simple. So basically, we're going to use the neural network policy as long as the next state, xt plus 1, if we use the neural network policy, is still contained in this recoverable set. And if not, we're going to use PyBackup. And if you it's not hard to show that this approach maintains the invariant that if we're currently in the recoverable set, then we're in the recoverable set on the next step. And by induction, we'll stay in the recoverable set for the entire horizon of the control problem. So we're going to ensure safety. And basically, the reason this holds, if we use PyDNN on step T, then by our check, we have already guaranteed that xt plus 1 is in the recoverable set. If we use PyBackup, then since we were already, if we use PyBackup on step T, then we already knew that xt is recoverable. So using the backup, continuing to use the backup policy from xt plus 1, we should still be able to safely come to a stop. The key challenge is that X recoverable can be hard to compute in closed form. If we had a closed form for X recoverable, we could just perform the above check. but we can't, and it's often really hard to compute. So instead, what we want to do is check whether X is recoverable using model-based simulation. And so this idea is really simple. We're basically going to simulate the system using to see if xt plus 1 is in X recoverable. So first, we're going to simulate one step using the neural network policy to get to xt plus 1. And then from there, we're going to switch to the pi backup and see if it can safely bring the system to a stop without running into the obstacle. And if it can, then this xt plus 1 is recoverable. But if we simulate it and it runs into the obstacle, then xt plus 1 is not recoverable. And as I said before, we're going to use the neural network policy if xt plus 1 is recoverable. Otherwise, we're going to switch to pi backup. So one remaining challenge is handling unstable equilibrium points. So recall that so far we've said that X is recoverable if pi backup can bring it to a state X naught where the robot is at a stop. But X naught might be an unstable equilibrium point. And this means that even if we get to X naught, we still can't guarantee safety because the robot might, if it's unstable, then we might leave X naught after some time. And so rather than just try to get to X naught, we're going to try and compute a safe invariant set G around X naught. And we're going to do so for the LQR policy pi LQR around X naught. So basically, we're going to linearize the dynamics near this equilibrium point and use the linear policy to do control. And now, rather than trying to reach X naught, our goal is to reach this invariant set G. And then if we can do that, we're going to use then the backup policy. We're going to construct it in a way so that it uses pi LQR inside this invariant set. And actually, outside of the invariant set, it can do whatever it wants to try to get to G. And we just need to make sure it uses pi LQR inside this set. So to compute invariant sets, our approach is pretty standard. We're going to try and compute a Lyapunov function. So here I've written down the discrete time analog since we have a discrete time dynamical system. And then as usual, the level sets of this Lyapunov function are invariant for pi backup. And our approach is going to be to reduce this to a sum of squares optimization problem. So we're going to parameterize v of x as a quadratic function with unknown parameters, p, and we're going to plug it into this sum of squares program. So the sum of squares constraint encodes the Lyapunov property. So it says that basically the Lyapunov property I showed on the previous slide holds. One thing to note here is that we do need to assume that the dynamics are polynomial, and you can use Taylor approximations if they're not. And one more thing to note is there is an additional constraint I haven't shown here, which enforces that the invariant set is contained in the safe set, because we want a safe invariant set. So this is all pretty standard. So we solve this optimization problem, we get our Lyapunov function, and then we can use it in the model predictive shielding algorithm I described above. So we evaluated our approach on the cart pole environment, where the goal is to move the cart to the right. So if you use the LQR policy, it's really good at keeping the pole upright, but we actually want to move the cart to the right to accrue reward. And the safety in this setting is kind of guaranteeing that the pole remains upright. So we learned a neural network control policy for this environment using a standard model-based reinforcement learning algorithm called backpropagation through time. It basically backpropagates through the dynamics to optimize the parameters of the neural network. And we trained it over a time horizon of n equals 200 time steps. And we're going to test in the same an environment with the same dynamics, but we're going to test it over a longer horizon than with training. And basically what happens when we do this is that the neural network, if you just look at the unshielded neural network policy, it does really well for the first 200 steps, but then it quickly starts failing. You can see it's just the pole falls over right at the end over there. And basically what's happening is that the neural network works really well on the part of the state space that it's trained, but after 200 steps, it leaves that part of the state space and it goes into some unexplored territory and it doesn't know what to do there. So it kind of falls apart. In contrast, if we just use the LQR policy, it's going to stabilize the pole near the origin, but it's not going to be able to move the cart to the right like we want it to. And finally, if you use the model predictive shielding policy, it's actually going to get the best of both worlds in some sense. So it's going to use the neural network policy as long as it's safe to do so. But the minute it can't ensure safety, it's going to switch to the to the backup policy and use that to stabilize the pole near the origin. And just to give some quantitative results, it shows basically the same thing. So here I'm plotting the reward accrued by each policy. So on the left, you have the learned policy without the shield. In the middle, you have the LQR policy. And on the right-hand side, you have our MPS policy. The unshielded, the learned policy achieves the highest reward, whereas ours is somewhere in the middle, and the LQR policy achieves essentially zero reward. And conversely, for safety, our approach and the LQR policy are both 100% safe, whereas the shielded policy is frequently unsafe. Sorry, the unshielded policy is frequently unsafe. So just to summarize, we've proposed a general framework for safe reinforcement learning that combines the neural network policy with a safe backup policy. And we also are working on extensions to more challenging settings such as stochastic dynamics, multi-agent systems, human interactive control, and others. So thank you for listening, and feel free to reach out to me if you have any questions.